Okay, we're going to finish up chapter 12 of conceptual physics. We're going to talk about arches, and let me dismiss my image. Why can't I see the cursor? There it is. Okay. Um, Arches. The roofs of some older buildings needed many supporting columns. Uh, they, they just had flat sections of these beams, and they couldn't take the stresses, so they had to have lots of columns to support. With the discovery of arches, supporting columns were no longer needed. Arches take advantage of the capacity of stone to withstand compression. So you can see these stones here. They they can take the compression very well. You can, I mean, you can probably find little videos where people take a piece of wood and stack these bricks on them, and then remove the wood, and the bricks stay in position. Uh, they use this ability of stone to increase the strength of the structure. So these arches are very, very, very sturdy, and they can withstand the test of time. Um, let's see. If the arch is supporting only its own weight, then the proper shape is a catenary. Example, the Arch of St. Louis. The catenary is also the natural shape of a chain that hangs between 2 points. So you can see that this young boy holding the chain, it looks like a mirror image of the Arch of St. Louis. And the Jefferson Monument, if you take an arch and rotate it, um, you get the dome. So there's columns supporting these flat pieces here, but the dome itself, it doesn't have any support columns on the inside. Um, I've been to DC. I've seen the Jefferson Monument at a distance, never up close. Um, DC is a interesting city. If you have a chance, you should go there. Okay. Scaling. Scaling is the study of how the volume and shape of any object affect the relationship of its strength, weight, and surface area. The strength is related to the area of the cross section, which is two-dimensional and is measured in square meters. The weight relates to the volume, which is three-dimensional and is measured in cubic centimeters. Uh, so For increases in linear dimension, the cross-sectional area and strength grow as the square of the increase. In volume and weight grow as the cube of the increase. So if you have length of one side, uh, uh, the length of of a side is 1 centimeter. The cross-sectional area is 1 centimeter squared, and the volume is 1 times 1 times 1 is 1 cubic centimeter. The mass is 1 gram. What's the surface area? Well, you have 1, 2, 3, 4, 5, 6. It's uh, 6 square centimeters. Um, so we'll see that we need that later on. Now, if you double it, the length of the side is 2 centimeters. The cross-sectional area is 4 centimeters. The volume is 8 cubic centimeters. I said I should have said 4 centimeters squared. And the mass is 8 grams. Now the length of a side, if you go to 3 centimeters, the cross-sectional area is 9 square centimeters. The volume is 27 cubic centimeters, and the mass is 27 grams. And if we go to 4, you see the length of a side is 4 centimeters. The cross-sectional area is 16. The volume is 64 cubic centimeters, and the mass is 64 grams. Now the surface area to volume ratio is, that you can do it 1 over the size, or I mean it's going to depend. We'll see in our example that it's not always 1. The ratio decreases with increasing size. The surface area of a 1 centimeter, um, 1 centimeter cube volume shown opened up is 6 square centimeters. The ratio is 6 to 1. When the volume of the cube is 2 by 2 by 2, it's 8 square centimeters, and the surface area is 24 square centimeters, and the ratio is 3 to 1. And when you go 3 by 3 by 3, the surface area is 54 and the volume is 27. You get a 2 to 1. Let's do this little quiz. If a 1 centimeter cube is 1 centimeter cube is scaled up to a cube that is 10 centimeters long on each side, how does the surface area to volume ratio change? Is it 1/100th of the original, 1/10th of the original, 10 times the original, or 100 times the original? Well, this isn't something I do in my head. I had to lay it out as an example. The surface area of 1 centimeter cube is 6 square centimeters. The volume of 1 centimeter cube is 1 cubic centimeter. And so the surface area to volume ratio is 6 to 1, 6. Now the surface area of a 10 centimeter cube is 600 square centimeters. The volume is 1,000 cubic centimeters. So its surface area to volume ratio is 600 to 1,000, so it's 0.6. So the increased volume ratio is 1/10 that of the original volume ratio, and we'll see that that's the answer B. It's 1/10 of the original. The surface area to volume ratio is approximately 1 over the size, and the size of the cube is now 10 times the original size. The surface to volume ratio will be 1/10 the original. I like doing it my way. This way it's a little more clear. And that's the end of the lecture.